Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Welcome to Lesson 12, Relationships Between Two Numerical Variables. Classwork. A scatter plot is an informative way to display numerical data with two variables. In your previous work in grade 8, you saw how to construct and interpret scatter plots. Recall that if the two numerical variables are denoted by x and y, the scatter plot of the data is a plot of the point x comma y data pairs. Example 1. Looking for patterns in a scatter plot. The National Climate Data Center collects data on weather conditions at various locations. They classify each day as clear, partly cloudy, or cloudy. Using data taken over a number of years, they provide data on the following variables. X represents elevation above sea level in feet. Y represents the mean or average number of clear days per year. W represents the mean number of partly cloudy days per year, and Z represents the mean number of cloudy days per year. Okay, so X is elevation, Y is average of clear days, W is average of partly cloudy days, and Z is average of cloudy days. Okay, so here's the table that we're going to use in this lesson, and it shows data for 14 U.S. cities. Okay, here's page 2. And a scatter plot of the data on elevation and mean number of clear days. So if we're talking about elevation, we are using the variable x. Oops, let's try pen here. We're using the variable x. And then the y over here is mean number of clear days. So this is the y-axis. I shouldn't say that because that would, in this case it is clear days, that's our y. But this could be the x-axis, and this is the y-axis. But if we were talking about partly cloudy days, this would be called the w-axis, but in this case it is the y. Okay, so we're using elevation above sea level in feet, and mean number of clear days, which is our y. So we're using these two columns here. That's why it's called bivariate data, two values. So Albany, New York was 275, and then 69 clear days. So that would be, so Albany, just for starters, here's 1,000. 500 would be here. 250 would be over here. So this point right here is Albany. Just to give you an idea. Albuquerque, New Mexico is 5,311, 167. So here's 5,000, here's 6,000. And 167 would be just shy of 175. This point here would represent Albuquerque. And that's how we plot this. We just plot the x and the y values. So this data was taken from these two columns, and these are the points that it created. Okay, so let's make this a little smaller. We can see all of the data that is posted here, just like this, x and y. So number 1 says, do you see a pattern in the scatter plot? Okay, or does it look like the data points are scattered? Well, if you look, they're kind of squeezed together in this vicinity here. So as you can see, they're kind of squeezed together, and that would look kind of linear. So they're in a straight line like this. We don't do the two lines, but I just wanted to show you that that's the range that they fell in, and the average line would be somewhere around here. So yes, there is a pattern in the scatter plot, and it looks linear. Okay, so here is a more detailed explanation. The scatter plot does not have a strong pattern. Students may respond that it looks like that the data points are randomly scattered. If students look carefully, however, there is a pattern that suggests an elevation increase. The number of clear days also appears to increase. Motivate the discussion by looking at various data points with the several at lower elevations and several others at higher elevations to indicate the possible relationship. So what they're saying is this point here is low elevation, low clear day, low number of clear days, and over here is a higher elevation, and it seems like as we're going to the right, as the elevation increases, the number of clear days apparently increases as well. Yes, you do have some that drops down, but on average, the group is moving upwards from left to right. Number 2, how would you describe the relationship between elevation and the mean number of clear days for these 14 days? That is, does the mean number of clear days tend to increase as elevation increases, or does the mean number of clear days tend to decrease as elevation increases? And as stated before, we would say as the elevation increases, the number of clear days generally increases. There are some days where it drops, like from here to here. Okay, this elevation increased, but the clear days decreased. So that was just shy of 4,000, and it was down to 82, so that looks like Helena, Montana. All right, number 3. Do you think that a straight line would be a good way to describe the relationship between the mean number of clear days and elevation? Why do you think this? Okay. So what we would say here is although the pattern is not strong, a straight line would describe the general pattern that was observed in the discussion of the first 2 exercises. So this is a positive, weak, or not, yeah, I'd say positive, not so strong or weak linear correlation. Okay, page 3, exercises 4 through 7. Think about linear relationships. Below are 3 scatter plots. Each one represents a data set with 8 observations. So an observation is an actual point. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, and so on. So 8 observations in each one. The scales on the x and y axes have been left off these plots on purpose. So they didn't put any scaling down here. So you have to think carefully about the relationships. Okay. So problem number 4 says, if one of these scatter plots represents the relationship between height and weight for 8 adults, which scatter plot do you think it is and why? So in other words, if we had a certain height or weight here, then this would be a certain height or weight over on this axis. So we could list this as height, and this as weight. Okay, and in doing so, does this make sense? A shorter person weighs less. As you get taller, your weight increases. That does make sense. If we use scatter plot 2 and use the same scales and put weight here and height here, okay, like so, then this would be as height decreases, weight decreases. Well, we don't generally shrink so much. You know, when we're born, we're like inches long, and then we end up being 5, 6, some even taller than that, feet. Okay, so we get taller as we get older, not shorter. So it would not be scatter plot 2. And this would be as you get shorter, your weight decreases, but then you turn and you get taller again. So that doesn't make sense either. So I would put that back over here. Oh, that was neat. And slide this over here. Okay. Now, if one of these scatter plots represents a relationship, which scatter plot do you think it is and why? So I would say it would be scatter plot 1. But it could be either way. Height could be the x-axis and weight could be the y-axis like I have here. Or we could flip them around. And weight could be x-axis, height could be y-axis. Okay, so scatter plot 1, weight or height could be assigned to either axis. As height increases, so does weight, or you could say as weight increases, so does height. Now, if we look again at scatter plot 3, we could also say weight or height could be assigned to either axis and that there is no relationship. It doesn't matter how tall you are, you can have someone heavy and short or heavy and tall, or light and short, or light and tall. So if you think of it that way, this could be a scatter plot for height and weight with no correlation between the two, or no relationship. Okay, page 4 brings us to problem number 5, or question number 5, and it says, if one of these scatter plots represents a relationship between height and SAT math scores for 8 high school seniors, which scatter plot do you think it is and why? Okay, so looking at this one, if this was height and this was score, as height increases, your scores increase. So you have a student in your class and they're 5 feet tall. Well, it's guaranteed that they're really going to do poorly on this test. They can't do well. And then there's this guy, he's 6 feet 5 inches tall, so he's obviously going to get the highest score in the class because he's tall. Does that make sense? No. Okay, so that doesn't make any sense. As you get taller, you don't get smarter. The other way around, and people don't shrink. So as you get shorter, well, I should say the tallest person had the highest score, and then as we pick values of people's heights decreasing, then the scores are going to decrease as well. That doesn't make any sense either. So where are we? We do not have these two, so I would say scatter plot 3. Okay, this is just random. There is no relationship between the two, so the solution would be scatter plot 3. Weight or score could be assigned to either axis. There is no relationship. Number 6. If one of these scatter plots represents the relationship between the weight of a car, okay, weight of a car, and its fuel efficiency, for 8 cars, which scatter plot do you think it is and why? So as the car gets heavier, it gets more efficient. Fuel economy. That doesn't make sense. The heavier the car, the more fuel it would take, the more work it would require to move that vehicle. Okay, and then if I moved those two over here, like so, as the weight decreases, the fuel efficiency decreases. Doesn't make much sense. And then if I move it over here, so as the weight decreases, fuel efficiency decreases. Well, let's think about this. Let's go back to this one. Let's put that there. All right. If we move this over here, like so, as the weight decreases, if this is weight, the weight's decreasing, fuel efficiency is going up. So if this was 10 miles per gallon, 15 miles per gallon, 20, 25, 30, 35 miles per gallon, with the lighter car, that's going to get more fuel efficiency. That makes sense. Okay, that sounds better the way I worded it that way. Okay, and then finally this one here would say that there is no correlation between weight and fuel efficiency. All right, there is a way you could argue that, and I'll explain that in a moment, but let me bring in the answer. Scatter plot 2, weight or fuel efficiency could be assigned to either axis. As weight increases, fuel efficiency decreases. So in this case, we're saying fuel efficiency increases, the weight is decreasing. But if we rotate these around like so, then now we're saying as the weight increases, efficiency decreases. Okay. But I would also look at scatter plot 3 and say that there is no correlation between weight and fuel efficiency, simply because there are other factors involved in fuel efficiency. The aerodynamics of the vehicle, the fuel distribution system. Is there a carburetor in it from the old vehicles, or is it fuel injected? Is it an electric car or a hybrid? Many different factors come into play with fuel economy now. So now it's not really necessarily directly correlated between weight and efficiency. So I would also consider scatter plot 3. No correlation between weight and efficiency due to other factors. All right, so number 7 says, let's get rid of these. Number 7 says, which of the three scatter plots does not appear to represent a linear relationship? So if I drew a line through these points here, this is called a line of best fit, with trying to get an average distance as small as possible, the average as small as possible between this point and the line's value here. That's the way we calculate these values. So there's a line there, and this one here looks like, if we drew a line through here, it looks something like that, and all these points are very close to this line. So those two are definitely linear. Positive linear correlation, negative linear correlation. But this one here looks more like if we had this like here, with these two outliers, this would be a exponential, not linear, and it also looks like a smiling face. Okay, so anyhow, this is linear, this one's linear, but this one is not. So bring in the answer. Scatterplot 3 indicates there is no relationship between the variables that could reasonably be described by a line. Okay. Next. Okay, now we're given a graph. X-axis age in years, y-axis number of cell phone calls. Notice there is this little squiggly line here, or this Z or whatever. This is a break in the axes. So notice the distance between 20 and 30, and 30 and 40, and 40 and 50, and 50 and 60 are the same. You want to have a uniform unit of measurement for your scaling. But 0 to 20 looks the same as 20 to 30, and that would be a distance of 20 instead of 10. So this just shows that there's a break, and we're not showing anything 10 to 0 is cut out because there was no data down there. All right, for starters, that's what that means. So I'm sure there's questions on the next page. Okay, here's page 5. I've copied the scatter plot from page 4 and put it below number 9 here. So question number 8 says, is there a relationship between the number of cell phone calls and age, or does it look like the data points are scattered? Okay, so again, if we look at this data and I draw a line like we have been doing, it looks like there is a linear correlation like so. And we could probably move that around a little bit to get it to fit properly. And then we have what are called outliers. These two here don't really fit on the line, but just those two would not make it non-linear. This appears to be a fairly linear correlation. Okay. So there is a relationship. Number 9 says, if there is a relationship between the number of cell phone calls and age, does the relationship appear to be linear? So the pattern is linear, like I've stated before. As the age in years increases, as we get older, 20 years, 30 years old, 40 years old, 50 years old, 60 years old, as age increases, the number of cell phone calls decrease. So a 20-year-old makes a lot more phone calls than a 60-year-old is what they're basically saying here. Okay, question number 10 says, this is a new scatter plot, by the way. Now we're talking about frying time in seconds and moisture content in percent. Okay, so it says here data source, all these people here, thermal and physical properties of tortilla chips as a function of frying time. So they're dropping tortilla chips into a deep fryer, and they're saying that the longer you leave them in the fryer, the less moisture there is in the chip. The drier the chip will be after they take it out of the oil. So it says, is there a relationship between moisture content and frying time? Or do the data points look scattered? Okay, well, if I'm looking at this and I were to try to draw this is what that looks like. Okay, so I can't really do a linear because it doesn't really fit that well. This point's above, all these points are below, and then this one's above again. And if I move that around or rotate it, it just doesn't seem to fit very well. See, no matter how I rotate that, it just doesn't seem to fit as a linear. Okay, so I'll leave that out there just for now. The red doesn't really fit too well, but the blue is really close to all those. But there does seem to be a relationship. As the fry time increases, the moisture content does decrease. Okay, so it just says, is there a relationship? Or do the points look scattered? And I would say there is a relationship. Okay, page 6 brings us to problem number 11. It says, if there is a relationship between moisture content and frying time, does the relationship look linear? So here's the graph again. I brought it in from the prior page, and I would say no, it is not linear, but it does look like a relationship. Okay, so here's the answer to 11. As the fry time increases, the moisture content decreases, but it is not linear. Actually, that looks more like exponential decay. Okay, moving on to scatter plot number 3. So the x-axis says price in dollars, and the y-axis says quality rating. So they're talking about a product. Data source is consumerreports.org/health. So they're talking about something about health. And then number 12 says scatter plot 3 shows data for the prices of bike helmets and the quality ratings of the helmets based on a scale that estimates helmet quality. Is there a relationship between quality rating and price, or are the data points scattered? So looking at that, does that kind of squeeze together and form a certain type of line, be it positive or negative direction? So can I do this, or can I, does that fit well, or is there a way to rotate it? Does that fit well? Or how about here, move it around? It just does not seem to have a good fit anywhere. The best one, if we were to call this linear, might be right about here, but these points down here are way off. These just look like they're just randomly shot around the board, if you will, and there's not much of a correlation or a relationship. So it's just a scatter. So there is no relationship, the points are simply scattered. So let me get rid of this line because it's not linear. Okay, so it's just scattered. Number 13, if there is a relationship between quality rating and price for bike helmets, does the relationship appear to be linear? Well, there isn't a relationship, so we wouldn't even consider the linearity. So in words, I would say, because there does not appear to be a relationship between quality rating and price, it does not make sense to say the relationship is either linear or not linear. If there isn't a relationship, then it doesn't have any specific shape. Page 7 brings us to the end of lesson 12. Review the lesson summary and go to your problem set.